Appreciate everybody's time today. Again, as Jeff had mentioned, my name is Bryan Hutton with Lubrizol. Been around the industry quite a long time. I'm still learning, never stops learning, and I'm really looking forward to our interaction today. As we go through, you may have questions. Feel free to answer them. I got a timer here. I'm going to stay on time. We're running early. Thank you. And so that means I get a little extra time. So, right? Is that right, Jeff? Extra? Okay. All right. So I wanted to kind of, again, you're going to hear so many of the same things, I think, as you look at a lot of our different presenters and what we talk about. So I wanted to do a little bit different. We're going to talk a little bit about why thermoplastics and what they are, where they come from, common applications, critical points for design considerations, as well as we'll touch on joining methods. How many of you, when you think of thermoplastics, do you think of fiberglass with thermoplastics? Just a couple? Or you guys shy? Okay. Versus thermosets versus thermoplastics, right? Thermoset, fiberglass being a thermoset, and most of you've kind of been experienced with those. So we're going to talk more thermoplastics. And you've probably seen numbers, and everybody talks about, hey, this is from the old NACE or AMP, did a big study. And when you start looking in the oil and gas industry, of course, thermoplastics can be a solution, but we tend to like to use alloys in a lot of places, right? We want to get to special alloys and high nickel content and different things like that to give us more life because of the robustness of metals. They're solid, they're strong, those types of things. So going to try to look at it a little differently here today as we try to combat this high corrosion effect that we have on metallics. But one of the important facts I like to continue to put out, and anybody who's ever seen me present before, is plastics are not the same as metal, and you can't approach them the same way as you approach metal. You just can't do it. If you do, you're going to cause a lot of problems. I like to tell people a lot of times that plastics, we're different. And when you think about metallics and you think about the plant environment, runtime is important. So let's talk a little bit about it again. Plastics are not the same as metals. You can't treat them the same. You can't if you have an issue, you can't just grab whatever's in your truck and try to put it together and say, hey, it'll work, right? Duct tape does a lot of good things, but you shouldn't see too much duct tape in your plants, right? If you do, that's a problem. When we talk about the different types, and I like to continue to talk about this over and over again, is when you get into your different types of polymers, you have your amorphous, your semicrystalline, your thermosets. And again, not getting into the science of all of that, but just understanding that they're different, right? Different materials have different properties, have different applications you can go into, different key points. And we talk about glass transition temperature a lot with our amorphous materials because everybody thinks plastics. There's a melting point. Well, technically, there is no melting point for amorphous materials, right? You just have what they call a glass transition. But again, different things that we work with, how we work in correspondence to that glass transition temperature actually matters. And the whole point of it all is you can't have everything, right? There's always a trade-off. We talked about resin layer thicknesses a little bit earlier, and we talked about, hey, why can't we just make it thicker, right? And as Kevin pointed out, there's trade-offs. When we get one thing, we give up another. And how we deal with that, right, and how it fits our applications is really, really important. Let's talk a little bit about history and where they come from. But when you start thinking about PVC, everybody's kind of heard of PVC. Well, it started in 1872 is when they first synthesized the PVC. But it wasn't until 26, which was my former company, BF Goodrich, that we actually learned how to actually use it, where we actually learned to synthesize it and develop it and plasticize and things like that people got into. And that's when PVC really took off. So it was back in 1926. It was 1951, right, when they actually developed polypropylene back at Phillips. So that's when polypropylene came along. In 54, that's when they came up with the high HDPE, right? And then it was in 58 that we actually came up with CPVC. We chlorinated the PVC. Of course, if we could go back, we wouldn't call it PVC anymore. We'd call it something different because the indications that people have about vinyl chloride and things like that, they think it's still there, but it's not present anymore. It's been synthesized away. But in any case, when we get into it, CPVC came around in 1958, so we've got a pretty good history there. 1960 is when Arkema actually developed the PVDF, the Kydar resins, and so And I say that, all of these that we talk about, it's about history and time, and in relation to steel. You see, steel's been around since 1850. So if you think about the standards, anybody use ASME standards? Yeah, everybody, right? When you start thinking about the B31 and following the codes, and I kind of call them the Bible, right? Those are your Bible of pipe design. That's where we all go to. That's our basis. Um, we've struggled a lot with plastics. You can see steel's been around a long time, but ASME didn't come out with B31 back in 1815, right? It was only the 1900s. So we still got a little ways. We're playing catch up with thermoplastics and thermal sets. But again, we're in the process. And so the NM1 standard, if you haven't looked at it, it's the first of the ASMEs on thermoplastics. Highly recommend you start to get it implemented into your specifications and standards and things. It's not perfect, but it's more uniform and more consistency if we're all starting to go by it, as well as the NM2, where we get into the thermal sets. And the idea of having a standard that everybody can follow to be more apples to apples is a huge deal, and I'm a huge supporter of that. I'm glad to see it. So let's talk a little about sustainability. You guys ever think about that at the plant? They talk about that a lot, right? But just to give you guys a idea, when we get into the vinyls and things that we work with in CPVC, is we're mostly salt, right? Brine or salt water, chlorine, which comes from the salt water. When you start looking at, most of your plastics actually come from off kind of the off products of refining petroleum. So when you start looking at crude oil and breaking it down and things like that, a lot of those streams that came off of on the way to make gasoline and those types are used for other things, in particular plastics. But we're a very small piece of the pie when it comes to the petroleum production and what people actually do with it. And this just kind of gives you an idea of kind of where we sit, so in sustainability and things. So there's a lot more we could talk about again in those areas. But getting back to the theme here about plastics, is that not all plastics are the same. And it's really important that we realize that you can't just lump everything together. Hey, I'm using PVC. Hey, I'm using PVDF, or those types. You need to know a little bit more. One of the things I've always seen at some of the facilities is that we all have a lot of job functions at the plant, right? You've got your engineering, you've got your procurement, you've got some of your reliability people, you've got your operations, and everybody's got to work in sync. But sometimes, and where this a lot of times becomes more evident, is when every facility has their norms. They have their normal contractors that are in house, and those contractors, after a few years, learn about, hey, this works and this doesn't work, and they have the specifics. And I've seen it over and over again over the past 2 decades, where when facilities change, they get new procurement people, or they get new things that come in, and they change suppliers, or they change the contractors because of insurance or whatever it is, and all of a sudden we start putting the wrong material in. And I've seen it. I know we have some people from Sabic here. I know we've got some OxyChem here. I've seen it at multiple facilities. I've seen it at Olin. I've seen it at Dow. I've seen it at a lot of different places. And it all comes back to is that specifications, which a lot of times people don't take the time to update. People don't take the time to put specifics into, or people sometimes overgeneralize, and it usually ends up causing problems. And it causes problems because now I've got valves in that don't have the right seats in them. They may they just don't have, they may have peak in them, but it's not the right grade of peak, or it has whatever. Those are the things we see a lot. And that's why when we get into specifications and things, and we get into how we call those out, it's really important to be specific when we need to be specific, understand quality specifications when we need to have them, and understand that it's important to convey those importances to your people that work in line with you as you turn it over, because you may do design and you don't worry about it anymore, and somebody else is doing it. And then I've seen it again over and over again when things show up to a job site. It's people don't pay attention on the installation side and say, hey, they told me to put this plastic stuff in, so I'm just going to put it in, right? And they don't know the nuances of what they're working with and how to handle it. And those things, again, can cause problems. So just understand, when we get into these systems, specifications, how we call them up, all those things. And we've started to see it in some standards, and I'm pushing for more standards where they'll actually say, hey, you may need to actually look at it a little closer, look at it from a manufacturer, which manufacturer you're using, those types of things. Make sure you comply with grades. I thank my friends over at AgGrew and some of the others too. They've kind of shared some of this information with me. When you start looking at different types of material, right, the PFAs or FEPs, the PVDFs, realizing that there's different grades. I know those guys at Dow always talked about, we want Kynar, we don't want anything else but that, those types of things. Because when you get into a lot of specialty areas, which I think everybody here is really in a specialty area, where chemical resistance is extremely important. If you saw my table in the back there, we got the little piece about our top 10 chemicals we work with. We've tested over 500 different chemicals, just like what Kevin was showing with resins and things like that. We look at the same thing with the things like CPVC or Corzan type materials. And understanding the grades is super important in there, because if you're using one grade of Kynar, it may work in one application, but the next application it may not work in for whatever reason. And again, it's not about it being a good material or a bad material. It's about it being applied in the correct application and understanding what it is. And when you start dealing with suppliers, hey, I need a 20-foot stick, I need some Kynar or whatever, and then everybody starts pushing around and they're going chaotically trying to find these things. That's when we lose a lot of that specificity that we have in the process, and that's how we end up getting in some things that we may or may not wanted to have. So. And you guys do have all these slides, by the way, they're in the on the little flash drive that you've got. I'm not allowed to use flash drives at Lubrizol, so, but they are on those. So, and again, resins. This is resin selection guide and things that they have in INEOS. Again, I say this because the resources are there. Sometimes you feel like you may be on an island when you go into thermoplastics. Understand that there are resources available to you. There are people that actually want to help. Not everybody. I don't sell anything, so I don't make any more money or less money because you want to use it or not use it. It's really more about, hey, if you have application, your success is our success. And for me, all plastics. I don't want you ever to put plastic in and it fail, unless you know it's going to fail. If you expect it to last 15 years, it should last 15. If it's supposed to last 20, it should last 20. Those are the type of things that we look at. So let's hit the standards. So when we start looking at the industry standards again, we always start with ASME. We got the B31.3. One of the things we like to talk about in thermoplastics too is the B31.3 and bonder qualification. You just heard for the last, I would say 40 minutes, but it was really 30, right? Or a little less than, about certifications and things. And I was joking earlier with some of the folks I was talking with about certifications, because when I was in the plant, I remember we used to do a lot of vessel entries, to do a lot of special cleaning and things like that in our vessels. And I remember we had chain hoists that we used all the time to lift people in and out and things like that out of the manways. And my safety guy came up one day and he started talking about certification for human usage. And I thought, what are you talking about? This is a 2-ton chain hoist. It'll lift any humans we've got, And he said, no, we got to have it certified by the safety department that it's good for humans. And I was like, okay, right? But that's, again, it's all the purpose, right? Is safety. It's about making sure everybody goes home at the end of the day. That's why, when I used to run projects and I work with my contractors, I used to have it all of my setups that, it may take up to 2 hours. I have an hour job, but it may take 2 hours to safe you in. You just don't know. But it's all, again, it's for the safety, right, and longevity of it and reliability. So let's talk a little more. NM1 I mentioned already. Again, I list these out because these are standards that we all should be referencing in our facilities. I know Lubrizol, we have around 60 different manufacturing sites around the world. These are things that we have to have in our specifications that we continue to push. And I want you to make sure you know about those that are around thermoplastics. So the NM1, the NM2 for your thermal sets. There's also an NM3. I don't talk a whole lot about it. It's like a big data book, the way I look at it. It's just specification after specification. So if you're doing a lot of stress analysis or you're doing a lot of detailed, Caesar work, then maybe that one's a standard you're going to like because the data's there. So when you start looking for coefficients and special properties, you'll see a lot of those listed for different materials. The AWS B2.4, is really important. Yeah, I've got a couple samples in the back of some just regular piping that we have, pipe and fittings. ASME 2.4 is your bonding. That's how we put it together, whether that's fusion, whether that's solvent cementing. It's a standard and guideline. It also shows you how you can certify in-house for your people, so your qualified bonders and things like that. So it'll actually address that as well. And then the RTP1, because everybody has vessels. So you start looking at your non-metallic atmospheric vessels, RTP1 is where you're going to go for that. And there's other standards. So I list a few more there. And again, it's in the files on the flash drive. You'll have this if you need it. So let's talk about common applications. These are some things that we see. That's what the sign is on my desk in the back. But common applications for us, at least for on the CPVC side and what we do with Corzan, is it always starts off with water. It sounds kind of elementary, right? But water we all utilize, whether it's potable water, whether it's non-potable water. I think we use 4 different grades at our plant, whether we recycle it. We used to go through the wastewater system and we clean the water, and then we'd send it back out throughout the plant, and all of our floor wash downs, some of our low grade cleaning. So there's always different things that we deal with. I was telling someone just here recently, DI water systems. So when you start looking at purification, demineralization, and things like that of your systems to create a more consistent chemical process, I've seen people still use carbon steel. And I know they're smart people because they're PEs, right? They're PEs, they're well trained, they've got experience, but they're still using things like carbon steel for DI water. And it's like, what's the point, right? I'm going to clean it up, then I'm going to put it back in carbon steel. And they're really good about it, though, because they started putting in clean out spots. So they actually started fabricating in places where they can go in and put high pressure hoses on and clean out all the rust that kept coming in and blocking up their lines. So go figure, right? Again, smart people, good facilities, not understanding the technology that they're actually using and not having the resources. So again, if you don't hear anything else or understand anything else from this week, I think it's that you have resources. That's what Maverick's all about. That's what a lot of us in the room and outside the room here are about, is providing you with the resources to help you be successful to achieve what you're trying to achieve as a designer, as a mechanical. So we did things like hypochlorite, bleach, HCl. We've heard about sulfuric acid, hydrochloric acid, sodium chloride, chlorine dioxide, nitric acid, hydrogen peroxide. And the reality is these chemicals really stretch across many different verticals when we start looking, whether it's hydrometallurgy, right? When we start looking at that refining process that we deal with. We were just working with a catalyst recycling center, lithium recycling centers. We've done a lot of those different things. Chlor-alkali facilities, we've been doing it for years, and we're continuing to grow and do more and more in these chlor-alkali type environments. But again, a lot of different options that you have with the materials. So 24/7. One of the things people don't realize with plastics, again, though, is that it's a 24/7 operation, right? Just like your facilities. It's not a 2 hours a day or whatever, right? It's 24/7 continuous operation for decades. That's the idea that we work with. So let's talk about a little bit about key selection areas. One of the first things I hear in a lot of facilities, mainly refineries, if I go into them, is the first thing you talk about is tank farms and fire situations and things like that we get into. Are you a fire safe material, or what do I have to do? What do I have to do special? Well, nothing, right? There's nothing special that you have to do because of plastics, because you're going to put it in a tank farm. But there are things that you have to do from an engineering design standpoint of understanding the materials, right? Whether that's expansion and contraction, whether that's the temperature limits. I'll show you a slide here in a minute on temperatures. But understanding what materials are there. This is a fire situation. Most people think if you had a fire, that if you use a plastic material, it's just going to basically drop all of its contents. Fire's going to hit it. It's going to go up like a blaze, like a little log you throw into the fireplace that just lights up and goes away. That's not the case. Some plastics burn more than others. Depends on the type of materials. CPVC is a fire safe material. Doesn't like to burn, low smoke development, that type of thing. You would want to replace this, though. Don't leave it in service for another 10 years after the fire. Go ahead and replace it. But we do a lot of different things. Any of you ever lived in an apartment? right? If you've ever lived in an apartment, you start looking around, or a hotel, when you go into it, you see the orange stuff, the orange fire protection piping. Almost most all your apartments in the U.S. now are using what we call our Blaze Master material. It's basically it's a similar material to our Corzan, except it's orange. It's built to an SDR schedule, and they use it for fire protection. And one of the reasons why is it has a charge just like that. And then especially if you've got a liquid inside, that liquid usually acts as a heat sink. And because of the thermal properties of the material, it usually is able to maintain its pressure bearing capabilities. The orange stuff has to retain 175 psi rating under fire. So as the fire goes on, it still has to hold 175 psi to deliver the sprinklers. Those are the things that we see. And just to kind of dispel rumors, people have a lot of rumors and perceptions of a lot of things, and a lot of times we get those from people that we trust and people that we know. But the reality is we get opinions from people that don't know. So it takes time to kind of unravel some of those things, unlearn them, and look at some others. Underground, we hear that a lot too. We have some of our facilities at Lubrizol. They love using this underground, but they don't want to use it above ground. It's like, come on, guys. But you can use it underground. I know a lot of facilities don't like to dig, but there are standards that actually exist, ASTM standards that exist for underground trenching and things like that. The one reminder I keep putting out there, though, is don't forget your trace wire, right? You're not going to find it with metal detectors later when you start looking to map out, hey, is there any pipes here? These plastic pipes won't show up. So you need to have tracers on them so you can find them later, if you need be, which I don't know. I used to update our underground at our facility in New Jersey, and I used to think, man, this thing's crazy, all the layers and all the different things we had going across. And I don't know if everybody's keep those up, but I found out when the EPCs come through and we do a lot of those as-built drawings never make it. It never made it to us. So sometimes we have some holes that we have to get into. So pure water production, I want to kind of just jump through a couple of common applications as we get through to kind of wind this down a little bit here. When we start looking here, we see our systems used a lot in the water systems. Again, pure water, whether it's DIRO, processed water. We also get into cooling water and things like that. Some of the common things we've seen is, a lot of things around cooling towers, effluent waters, water treatment areas, chemicals. Again, all your chemical transports and things, because of our ability to go through really the full pH swing of your whether it's acidic or your caustic, kind of makes us a pretty good fit in a lot of these different areas. So I just want to show you a little bit of that. Drying towers. You guys have drying towers in a lot of these facilities, the places we've seen. Also collection headers and things like that. So we've pretty much, if you can draw it, you've got people out there that can fabricate. So whether that's tanks, whether that's special configurations, piping systems, things like that, they're out there. Show you a little bit more diversity. Here is the marine offshore. I don't know how many of you go into tankers and things like that, right, at a lot of your facilities. But we actually were the first of the thermoplastic, or the CPVC, to actually have a U.S. Coast Guard approval, where we go off because of the fire safety and things like that. We're able to go through with U.S. Coast Guard, and we've been used on a lot of platforms and ships and things like that for package units for decades. So when we get in, and again, fire safety is always a big importance there, but also purity. So let's get through a little bit on design again. This is the acronym I use all the time, PTM. I add the Q on there for quality. I think that should be a theme this week. Again, is the quality of what we do. But pressure, temperature, and medium is always a must, regardless of what you're working with for plastics. You got to look at them all together. Don't just look at pressure. Don't just look at temperature. You have to look at pressure, temperature, and the chemicals that we're working with. I think we talked, Kevin, and some of the questions that came up, we're talking about like sulfuric acid. Sulfuric acid is one of those kind of oddball chemicals that can do different things to different materials, right? If it's 98%, just use carbon steel. It's not corrosive, not an issue. But also, if you ever, who works with sulfuric acid? Yeah. What happens when sulfuric and water come together? Is it a nice exchange or what? No, it's a mess, right? I remember I was in Guadalajara actually a few years ago, and I was looking at a facility, and I've never seen this before, but they kind of had a water softener, a homemade water softener, and one of the things they were doing, I'm just watching, is they had a big tank of sulfuric, and they're just throwing water in it, and it's just boiling, and I'm like, this is the weirdest thing I've ever seen, because it's just going, but it's pretty violent. right? It's a violent interaction that actually takes place. But sulfuric's kind of a weird thing, because when you start looking at the concentrations, again, non-corrosive at high concentration, extremely corrosive as it comes down, right? And we use it a lot in chlorine applications and things to kind of clean it, or dry it, I should say. But when you look at it in different areas, so it matters. It matters. Temperature matters. Concentration matters. It's just a perfect example of, you really need to understand your process and what you're doing, so that you can get the expected life that you're looking for. So pressure, temperature, medium, and then you add in the quality side of, okay, just make sure it's consistent, because quality matters. There's different people you can get things from a manufacturing standpoint, especially in thermoplastics, where one manufacturer's material is not equivalent to another manufacturer's material, even though it's supposed to be the same material. And so fabricators can tell you a little bit about that, things they like to work with and not work with, and things. So, but we've seen it. Data, we've got tons of data. You can see a lot of our, properties. When you look at consistent properties, most of your thermoplastics, they're going to typically be pressure rated and things off of mathematical equations and things like that, because of the consistency and how they're made. A lot of times when you get into your thermal sets, they'll hydro test every piece, just a little bit different. You need experts, like Maverick, like some others that do design work, to actually design those resin layers correct, pick the correct resins, cure cycles, those type of things. So it's a little bit different with thermoplastics versus thermal sets, because of consistency. But there is a lot of data, and this question at the end is, as a plant guy, I just say, well, that's all great, but does it work? All I want to know at the end of the day is, does it work? Does it fit my need? And can I use it and sleep safely at night, knowing that I've selected the right material? And we'd like to say, and of course, that is yes. Bleach is another one of these areas that we do a lot of work with, and bleach is one of those materials as well that's not always stable, right? We get more and more concentrated now, where we want to concentrate it to 21%. Some people refrigerate it a little bit so they can get it up even more, so that when we ship it down the highway, we're not shipping water, right? So we want to get the concentration up. We go to packagers, and packagers repackage it. But I had an instance where, whenever you use hypochlorite, it's always going to off gas. It's going to break down. It's going to create a gas. It's going to pressure erase. So you never want to have dead areas in your lines. You always want to have some way of egress for your gases as they come off of the materials. So understanding that just means, again, you accommodate that in your design. I've seen one where we had it blocked in, and they actually overpressurized. It was so long before it was in a loading area, and it sat there long enough in a hot Texas day. It built up enough pressure, and it actually burst the line. And they said, oh, well, we'll just put Hastelloy in. So we just changed it to Hastelloy. So we went from a small bomb to a bigger bomb, right? But it didn't change the design. We didn't fix the actual problem. But again, hey, it's temporary, right? Everything in the plant, if it's temporary, right? I don't know. My saying the plant was temporary was permanent, because usually once we put it in, we're not touching it until it fails, because we got too much other stuff to deal with. So we'll deal with that again when we have to. We just push it down the road. So it matters. Pressure ratings. I actually had a valve sample in the back and things. And one of the things I like to show people on thermoplastics is, we get into issues where people don't quite understand the pressure rating of the materials. Not everything's pressure rated the same. So when you start looking at your flanges, you look at your pipe, your valves, you start looking at special components that you may have in there. They're not all pressure rated the same. And of course, when you do design, your system is only as strong as your weakest point. So just to be able to understand that. So, and then when you get into derating, we derate a lot of our materials, right? As the temperatures go up in plastics, we typically derate it, so the pressure rating goes down. Understanding those things actually matter. How it's built. We here in the U.S., our Corzan materials are all ASTM driven, so it's Schedule 40, Schedule 80 materials. It's designed to match up with steel. Because it's designed to match up with steel, what happens is that every size has a different pressure rating. If it's built to an SDR schedule, that actually changes. With an SDR schedule, the pressure rating is the same regardless of the size of the pipe, but it's still derated. But it's just the way that the thicknesses of the pipe are generated. They're based off of that dimensional ratio versus the schedule 40, schedule 80. So it's understanding that. Also, a lot of the people we deal with, deal with global standards. So sometimes we get people coming from Germany, or we have people in Austria, or we have design centers that are in other parts of the world. And so if they're designing in metrics and ISO standards, they're a little different than our ASTM standards. Dimensions for your flanges, things like that can be different, whether it's a DIN standard or it's ASTM. So understanding those differences is really important and how that can affect it. So when we get into long-term, performance of the materials, and this is something pretty common, hydrostatic design stresses are one of the things that we deal with in the vinyls. That's what actually generates your pressure ratings that you have. And in case anybody was wondering, like the pieces of pipe on the table back there, those are all pressure rated, and they're actually designed for 50-year lives with safety factors of 2. So that's the theoretical, right? We don't say promise everybody it's gonna last 100 years, but it's in applications that we say it works in, it's gonna work a long time. There's other applications where it's not gonna last quite so long. It just depends on them. So understanding what that is matters. I start talking about pressure testing because I've seen a lot of issues with a lot of commissioning and things too, where when you look at the ASME, we get into 1.5 times your design, and most people just design at 150 just because they design at 150. With plastics, you typically, or at least with thermoplastics, and what you'll see in the manufacturer literature is if we're looking at just straight non-reinforced, is we actually look off of your operating. So it's your anticipated operating pressures, and then you go 1.5 times that, not 1.5 times your full design, because again, we're not going to put 400 psi or whatever it is on these systems unnecessarily. And so it's just a little difference. It's just understanding those nuances, and that's why I bring it up today again. Just things that we want to make sure we look at in commissioning and things of non-reinforced materials. Ball valves, this is just a quick example of how when you get into, we talked about hypo a little earlier, and we get into ball valves, they have vented ball valves for things like hypo so that we don't have trapped materials that are going to create pressures and things. So those are some of the things that we get into. Designing for your specific requirements. I think that's why you guys are all here anyway. That's why we need people like Maverick, is that we got to be specific for what we're dealing with. And sometimes we need that extra support to make sure that we've got it right, so that again we keep people safe and we get the life that we're expecting. I like showing this outdoor. Eventually, I'm going to get a better graphic. I ain't got it yet. But when we get into radiant heat, a lot of outside installations and things, right? Everybody's got an outdoor pipe rack that everything's running through. And one of the things is really important to understand is that your atmospheric, right? People always say, "Hey, what's the temperature?" Well, it's just atmospheric, right? Or it's just the norm. Well, that's a huge variance depending on where you are in the world or what that is. But in addition to that, the solar heat that actually comes on the pipe racks and things, we've actually shown that your actual surface temperatures of your piping can be substantially higher than your ambient day. So an 80-degree day, you may have a 110-degree pipe up there when you start looking at surface temperatures and things like that. And this is why most people, if you've ever used PVC, usually as soon as you put it outside, you're already at the 140 limit, right? Just from a 100-degree day that comes through. And people don't realize, well, why does it sag or whatever? Well, that's why. Your radiant heat. Now we've got all the fancy guns. We can sit up there and just kind of point at it and get a surface temperature. Go check that out on a warm day. Go take a look at your pipe racks and look at some of the surface temperatures. And what you'll see is what I'm talking about. It's a true thing, and that's just something that you want to take into consideration. I typically tell people if they're running this outside, just design for 140 degrees, even though that isn't where it's at. And you just look at that from an outside temperature standpoint, because those are your possibilities at what can happen. Sometimes in your vessels, you may monitor your temperatures and you can keep it below that, whether you use a deluge or whatever. A lot of these facilities, especially like the chlorine guys and things like that, on the spears and things they may use deluge to keep the temperatures down and cool off the tanks or whatever. But it does matter. And this is just kind of a different graphical of that, of what we see when we look at things like other materials, some of the polypropylenes and things like that out there. When you look at temperature capabilities and pressure capabilities, all that matters. So let me run through a couple of quick things here on design, and then we'll be done. Thermal expansion and contraction is something we always design for, regardless. Don't just say, "Hey, I'm not heating the material" or whatever. We always design for it. We always want to take that into account. regardless. Sometimes it's just construction cycles. Just because I'm doing a project and it takes over a year to build it, so I'm going from summertime to wintertime, and I'm going through these different transitions. And so putting a loop in to make sure that you don't get the crazy looking pipe is important. Making sure that you're keeping the stress off of fittings and those types of things, because again, it can be a mess when you start getting into it, and we don't want any of those situations that you see on the screen there, right, where you pop you break a fitting or something because it expanded and it was just too much stress on that particular joint. So that's why we do stress analysis, right? Stress analysis, we get into the proper supports at the right places. We get into supports that don't actually cut into or damage the pipe. All that stuff matters. You can't just take one material and throw another one in there and say, hey, it's going to be great. 9 times out of 10, maybe it is okay, but you don't want to get caught on that 10th one, right? We don't want to be that person that has to deal with those kind of issues. And so making sure we kind of take the stresses in, understand the difference in thermal expansion and contraction, super important. So the number one problem we have in thermoplastics, especially CPVC, though, is actually the welding process. And this kind of goes back to what we were talking about earlier on certifications and things like that, and training. Training's available. Most people do it for free. It doesn't cost them. It's always a time commitment. That's where it costs people, is just the time commitment and the understanding that they need it. But when you look at amorphous materials like the vinyls, our whole thing is built off molecular entanglement. How these long molecules change, how these polymer chains actually intertwine together. And when we go into a thermoplastic welding process, we're taking two materials, we're basically applying some type of heat. That's what your primers and solvent cements are, in essence, they're heat. When we put them together and we bring the two materials together, and those molecules, polymer chains, I should say, they intertwine, and that's where your strength comes from. That is the number one area we typically have issues. So when we talk about welding processes, the solvent cement welding is the number one process, and we do millions every year. There's 2 to 3 million solvent cement joints done every year in the materials. It's a very widely used thing. Hot gas welding, some of you may have heard of that. Hot gas, sometimes they use that in the fabrication or the follow-up. Heated tool butt welding. So you've got the butt welding type of tools. Now we're seeing more and more, and we've got some new ones coming, some new vinyl fusion machines that are coming to the U.S. now that they're actually doing pretty well on the fusion side. So your CNC machines, socket fusion, as you'll see on some of the other materials as well, not us, but electrofusion for some of your polyolefins and things, IR welding, friction welding. You guys have all seen these, right? Ultrasonic welding. It's all ringing a bell, I hope. But let me finish up here on basic principles of solvent welding. And this is really important for a lot of people that do global work. Again, is that if you've used some of the materials, some of the UPVC, or used some of the other materials from other parts of the world, the ISO standards aren't the same as far as the dimensional setups as what we see on the ASTMs. And so with the ISO, all of your fittings, they're more of a glue. They're not a tapered. In the U.S. here, all of our fittings are tapered. That tapered fitting, meaning that the socket size actually gets smaller as we go down to the bottom of the socket. That's why getting full socket depth matters, and that's why we try to make sure people understand the training of it, because in order to get that molecular entanglement that we talked about earlier, you kind of have to have forces that pull it together, and this is a mechanical force that we use. So this is why we call it a weld process and not a glue here in the U.S. The ISO standard is more of a glue. This is not in the U.S., so that's why it's important. So that's why there's different feelings of people in Europe that we've seen versus in the U.S. That's why our results have been dramatically different in what we see in a lot of these materials, because here, in instances like this, the solvent cement should never see the medium itself. The material should, not the solvent cements themselves. So just a little bit, and we've got more, but not for today. So in conclusion, thermoplastics, of course, they're here to stay. I don't even think we've announced it yet. We're getting ready to build a new facility in India, of all places, to create more materials. We've got a global consumption is definitely on the rise. Applications are growing, all right, because of the different things that are coming up. The hydrometallurgy is really hot right now. lot of things going on, whether it's on the mineral extraction side, or the or even on the recycling. We're seeing a lot of recycling type centers, so they can recycle a lot of these precious metals and things like that here in the U.S. So sound design is a safe, long performance, and that's important to understand that. And everybody in the room is part of that, right? It's part of the specifications, part of the material selection, part of the ensuring the safety and integrity of your facilities. And it's really important that we all take that to heart and stick with it. So